Okay. Happy New Year, everyone, and welcome to our first seminar in 2019. Today we have our own Johan Knapen. Johan did his PhD here a few years ago, and then he moved to Canada and Liverpool. And since more than 10 years ago, he's back at the ISC as a staff. But for the last few months, he's been working in Liverpool with a sabbatical. So he will be there until July. But today he's here with us, and he's going to present a breaking news seminar about his latest result with the adaptive optic mode of MUSE. So thank you, Johan.
Good. Thank you very much. Good morning, everybody, and Happy New Year. This is the first seminar in the year, so it's my honor to give that. This is a very short talk about a very short paper. This is an ANA letter that was actually we were sent the PDF yesterday. It's just out. And this is based on science verification data that we got last summer using the adaptive optics mode of MUSE, the integral field spectrograph on the VLT. So this is in collaboration with two ex-PhD students from the ISC, Sebastian Comeron, who is now in Finland, and Maya Seidel, who's in California. So with the three of us, we got this, we got the data, reduced it quickly, and wrote up this quite interesting paper. So this is about a galaxy NGC 7130 that's known as a composite AGN, which means it's got an AGN and it has a starburst roughly in the same central region. So why is this interesting? It's got to do with incretion onto supermassive black holes, which is closely related to galaxy evolution. We all know about that the supermassive black hole mass scales with the properties of the galaxy and the bulge, which is strange because the spatial scales are completely different. A black hole accretion occurs basically on AU scales, and galaxy scales are many kiloparsecs. So it really is very puzzling why those two parameters, or those sets of parameters, both the black hole and the whole galaxy, should be connected, but they are. So that's a puzzle. This can result either from feedback from the AGN, which then goes back into the galaxy, or it can all be a consequence of cold gas availability, which then scales both the galaxy and the supermassive black hole. So that's a big puzzle. A key parameter here is gas inflow. There's enough gas in the disk, and we need a tiny bit of that to fuel the AGN and also the starburst if we have one. But this gas must lose by far most of its angular momentum to get to the tiny scales of the supermassive black hole. And that's a big problem in how to get rid of that angular momentum. There are ways to do it, mostly to do with non-exosymmetries, bars can do it, etc. But again, the supermassive black hole scale, the AGN scale, is so tiny that this really is a problem. Gas, if you do manage to get it all the way into the center, can of course lead to both AGN activity if you drop it onto the black hole, and it can also cause star formation activity, and it can happen in the same galaxies, as we'll see. So key to this is then the study of the gas physics, of the stellar properties, and the kinematics of these what we call composite galaxies, which both have AGN and starburst activities. So that's what we're doing here. We chose one galaxy, NGC 7130, and we'll hope to do more. But these are interesting galaxies because they have both the AGN and the starburst, and it really allows you to look at the physics in a bit more detail. So here's our galaxy. This is, as I said, a composite AGN starburst. The distance is 65 megaparsec, not very close, but reasonable. 1 arcsec is 300 and a bit parsecs. It's classified as a peculiar SA galaxy. It's a LIRG, a luminous infrared galaxy. It's a Cepheid 1.9, and quite a strong one sitting in the center. And it's got a compact circumnuclear starburst, which is actually a little ring, a tiny little ring sitting in there. So on the left we see the HST image of the central part of this galaxy, or most of the galaxy. This is from about 20 years ago, published by Rosa González Delgado and collaborators when she was at Johns Hopkins as a postdoc, I think. So that's the HST image here on the left. And you recognize basically this part coming back on the right. This is again the HST image that you see here in black and white. And overlaid on this is the little box that shows our MUSE field of view, which is a couple of arc seconds. This is what they call the narrow field mode of MUSE. It's not the standard mode that most of us have been using so far, which is about 1 arc minute field of view. This is a few arc seconds, but we put it there in the center. So, a little bit about MUSE. What we did is put in a proposal and then obtained science verification data with MUSE in this new narrow field mode. MUSE, as all of you should know and most of you will know, is the integral field spectrograph on the ESO VLT. A huge instrument, very productive, brilliant thing. MUSE-NFM uses an adaptive optics system called GALACSI, which consists of 4 sodium laser guide stars, a deformable secondary mirror, and an infrared low order sensor, and that provides near diffraction limited resolution in the optical. It's a spatial resolution. So we used the Seaford nucleus of the galaxy as a natural guide star to measure any remaining atmospheric tip tilt, defocus, and astigmatisms. Standard AO uses a star to correct the deformation by the atmosphere. So you look at the star, see how the point source reaches your detector, and on the basis of that, in a very fast feedback loop, you correct the image of what should be a point source to actually be a point source, and that way you can take out the atmosphere effects. If you look at things that are not stars, this is more complicated. So this is for our galaxies is the case. You can use the center of the galaxy, but it's not a point source. So you can still correct with AO, you can still correct on that, but you don't get to the same level of correction, and that is if you have something that looks like a point source in your galaxy. What you can also do is find another star, or not another star, a star near your galaxy, and correct on that star, because then you know it's a point source and you correct that. The problem with that is that the patches of atmosphere that show sort of coherent changes are quite small. So you need your guide star to be very close to your target. And this is arc minute, arc seconds, arc minutes, I think. So you can't use any star. You need bright stars for this correction, and in practice that doesn't work. So what you do is you make your own star, you take a laser and you project a star in the sky, typically on the sodium layer about 80 kilometers high, and you make an artificial star where you want it, and that can be very close to your guide star. So why do we use 4 sodium laser stars here? It's because the patch of atmosphere that you correct is smaller than the size of an 8-meter mirror. So if you have an 8-meter diameter mirror, you need 4 lasers to correct, because you have basically 4 independent patches of sky that you need to correct for, hence the need for 4 lasers. If you have a smaller mirror, you could get away with 1 laser, which is what they've been using on the Herschel telescope here on La Palma. So that's why you need the 4 lasers, and then you still need a natural guide star, which doesn't need to be as bright and doesn't need to be quite that point source. So that's why we can use the Seaford in the center of the galaxy to do this. So to set this up is quite complicated. You need a suitable natural guide star, and then of course you need to run your 4 lasers. So this is why we chose an AGN to use this. So here's MUSE, sitting there on one of the Naismith platforms on one of the VLT telescopes. It slices an image of roughly 1 arc minute size up into many different bits, and all these different bits go to parts on the detector, actually on 4 different detectors. And so you slice the image and you slice it more, and you end up with, I forgot how many spectra, but a lot per image. How many, Mohammed? Anyway, many, doesn't matter. So this is what Galaxy looks like from a Durham University press release. So these are the 4 lasers shooting from the edge of the mirror. So you see the telescope in there. And I don't exactly know where the lasers are mounted, but it looks like they're on the secondary ring here. Don't know if anyone's been there while this was operating from here. I've not. So this is what it looks like from outside, wider side, and this is what Galaxy looks like. I'm not an expert on Galaxy, I just got these from the web. it's mounted here. There's the Naismith adapter. Telescope is to the left. So it sits in there. And then the MUSE instrument with its 24 spectrographs sits behind there on the Naismith platform. And then the part that you don't see on this picture is the 4 lasers with the associated optics. Let's look at this one. So here's the light coming in from the VLT, and this is the light going to MUSE. This is the actual AO systems. Those are the 4 lasers with the optics associated with it. And then here we've got all kinds of beam splitters and mirrors. Here's a calibration unit. There's a tip tilt sensor unit there. So this is what's inside that green box here. And this is a bit small to show, but it's basically the same. So this works. That's the great thing. Galaxy's been in development a long time. MUSE as well. MUSE has been working for a couple of years without the AO, but the combination works. So this is what we got. This is the integrated image. So we reconstruct the image from all the spectra, just add them up in the spectral direction. And this here on the right is the image that we get with the center there, and this little circle is where we think the circumnuclear ring is. And this is compared to, on the left, the Hubble image that we got from the archive. And if you look at little blobs like the ones up here are the ones up there, and these on the lower right, you can recognize them very well on the HST image. So you see that the resolution that we get with MUSE adaptive optics really is very good, and we think it's around 0.15 arcsecond, which is about 400 or 450 parsec in our case. So this is really working in the optical. This is an optical image here. The contours overlaid here are CO, ALMA CO at roughly the same resolution from the literature. You see that the CO traces the dust lanes, which we see in the MUSE image as well, going up and down into the nucleus. So this really works. The AO system works brilliantly well. This is a fantastic image with very high spatial resolution. But, of course, this is the whole point of this. Behind this image, we got for every single pixel the full MUSE spectra. Because, to obtain an image like this is a bit boring because we have it from the Hubble. But the strength is getting in all this spectral information from MUSE. So again, a bit comparison with the HST data. This is the MUSE image again. And this little region is the one that González Delgado et al. In '98 highlighted. So this is their UV image in the middle, and on the right is their optical image. And if you look carefully, you can recognize these sort of course you have to compare optical with optical, and you can recognize these bits of emission that they identified back in '98 on the basis of the HST image. You can see them sitting up in that same area. So this is proof that the AO really works, and it really does correct the seeing. I should say that we got 10 sets of observations, 2 of which had natural seeing of about 0.55, and those are the only 2 that we used to derive this. The other 8 had natural seeing of about 0.8, if I remember well, and that's basically useless. They go in the bin, because the AO does its best, corrects them to about 0.6 or 0.5, but if you want to use this, you need good natural seeing, and then the AO system works brilliantly well. So let's look at the spectra then, what we get from there. So this is a composite of some emission line maps. So here we have H beta, O3, H alpha, nitrogen 2, and 2 sulfur 2 lines added up. And we see the morphology basically as we expect, because we know this from the HST, UV, and optical data, little patches of star formation and a strong point source, which is the AGN. Combining H alpha and H beta, we can get an extinction map, which we then can compare with the CO. The CO molecular gas traces the dust, and we see that indeed in this image here. So these are the kind of images that we get from the MUSE cube. Those images we can divide on a pixel by pixel basis. We get these diagnostic diagrams. So what we see here horizontally is the N2 divided by H alpha. So that's one line ratio, and we plot it versus another line ratio, which is O3 over H beta. The advantage of doing this is that you divide out the dust effects These are both blue lines and these are red lines. If you plot H beta versus H alpha, you have to be very careful about dust extinction, but you divide most of that out by doing this. So you get these what's called diagnostic diagrams. Our points, our measured points are here. They're color-coded basically from blue down there to red up there. There's no more to it. It's just where they are in the diagram that determines the color. This region here below this curve is known from models to be down to star formation. This region up there is known to be down to shocks, which can be either shocks to do with star formation or, as in this case, mostly shocks to do with AGN emission. And then the region in the middle is a transition zone where you can have a combination of star formation and shocks. So this is a well-known technique that you can use. What we can do, because we have all these individual points, which are all individual pixels, and we can map them back into the image, which we've done, and what you see on the right is all these individual points then mapped back to the spatial position where they're from. So here's our MUSE field of view again. The cross in the middle is the AGN position, which we define by peak in velocity dispersion. The blue regions are out here. That's the star formation. That's where you expect it to be. And the red is sort of concentrated around the center. But then there's this region up here, all the way to the northwest, which is not symmetric. And it's got AGN-like shock characteristics in the line ratios. So that's a weird area all the way up there, which we identified, we discovered, and we'll see a bit more of that. So that's the line ratios. Then we got the kinematics as well, of course. So here's the velocity field on the left, and the position of the center is there, and the velocity dispersion is on the right. And I already said that the peak in velocity dispersion, which you see in the inset here, that's what we use to determine the AGN position, and tie it then into the astrometry with the ALMA data, etc. Velocity dispersion rises roughly towards the center, with a little area here which is star formation. But again, this same region where we saw the strange line ratios and the AGN-like line ratios, that same region shows enhanced velocity dispersion. And then if you look on the left here, that same region again shows weird velocities. The velocity field runs roughly from high values down here to low values up there. That's what we also see in the ALMA data and the CO data. So the gradient is roughly left to right here. But then we got this plume in the same direction where we saw it here, and the same area where we saw the strange line ratios, that has relatively low velocities. So there's something going on in that area. We think it's a jet, a one-sided jet from the AGN. The other thing I want to highlight here is this little area, which is the inset. It comes from here. So this is 1 arcsecond by the side now, this little box. And we see here a tiny little area of positive and negative relative velocities, which we think is a kinematically decoupled disk with a radius of about 0.2 arcseconds. So that's one here. So, two discoveries from this. The one is this area northwest of the nucleus, an extent of at least 2 arcseconds, or 650 parsecs. I say at least because it reaches the end of our field of view, so it might continue further, we don't know yet. The line ratios are indicative of shocks, presumably AGN related, because there's no star formation there that is much more there or differently than in other regions, so it looks like it's AGN related. Relatively low velocities, enhanced velocity dispersion. There's no counterpart to this region at all in the UV, not in the optical, not in the infrared, and not in millimeter emission in ALMA. It's also not seen in a dust extinction map. So on the basis of all of that, we say that our preferred interpretation is a one-sided jet outflowing from the AGN that goes in that direction. The orientation is 90 degrees from the line of nodes, as we know from the velocity field. And that's interesting because then if you speculate that the black hole rotates in the same way as the galaxy, then you'd have polar outflow, which you could have, but this is an assumption that we make. But we think we discovered this AGN jet, a one-sided jet. The other thing was this mini disk. which is a tiny kinematically decoupled core. These are not rare as such. They occur in about 1 in 10 early type galaxies, so they're quite often seen. These kinematically decoupled cores, little regions in the center that rotate differently than the main body of the galaxy. And it's traditionally interpreted as a remnant of past interactions in a galaxy. So here we see it as a region of 0.2 arcsecond in radius, about 60 parsec, with distinct positive and negative velocities. This area surrounding the peak in velocity dispersion, which indicates the nucleus and the AGN position. The kinematic orientation implies that it could be related to the jet. Let me try and go back here. So the jet is in this direction, and the decoupled kinematics is roughly in the same direction. So this could be a continuing structure, but that's pure speculation. It could also be, of course, an independent and quite small nuclear disk, which is rotating in a different plane and may result from a previous interaction. This is like a traditionally decoupled disk interpretation. So it may or it may not be related to the AGN, and that's speculation, and you can choose what you prefer here. So, on to the conclusions. We've observed the core of this AGN-starburst composite galaxy, NGC 7130, with the new MUSE narrow field mode adaptive optics system. We reach exquisite spatial resolution, similar to HST, about 0.15 arcsecond in the optical, coupled, of course, with this full spectroscopic power of MUSE. 2 discoveries from this short observation of one galaxy: an AGN-related jet, which is one-sided and at least 600 parsec long, seen as a plume of low velocity, high velocity dispersion material with AGN-like emission line characteristics, and a tiny 60 parsec radius kinematically decoupled core region, which indicates a tiny inner disk. And future work on this data set includes the analysis of the gas physics, the stellar populations, as well as kinematics, and that will be done in conjunction with some GAFAS data that we obtained. Now, if you want to work on this data yourselves, you can. It's all there. Science verification data are immediately public, so they've been public since I think August. So go ahead or talk to us. But we plan to write 1 or 2 more papers on this, and hopefully then go on to observe more galaxies, because this really is very exciting. So that was all. Thank you very much.
Questions?
Great stuff, Johan. So I was wondering, did you have a look at how this source looks like in X-rays? Is it something that you have checked?
I haven't yet.
Interesting to see whether there is a connection.
Yep.
And the other thing is, I mean, you're going to be working on the stellar populations, but could you anticipate any results on what type of stellar populations you get? I mean, are you getting anything interesting there, or so far?
No, we haven't looked at it yet.
Signal to noise is good in the continuum?
Yes, yes, it should work, but we just haven't. We've been concentrating on this so far, so we haven't got there yet. But it should be. The data is beautiful. It should be in there. Looking forward to it.
Hello. Has the jet been observed in radio, for instance, or is?
I haven't found radio observations of this galaxy, so we don't know.
It should be interesting to observe in radio to really find a very strong evidence of this feature.
Certainly, yeah. And if it's anywhere, it should be in radio. I mean, so yes, I agree, but I haven't yet found radio data.
Two short questions. So the first one is, do you have any idea of the mass outflow rate associated with this plume or this feature that is blue shifted?
No.
Because that's really the important, well, it's one of the important the key points. And the second is about the physical mechanism of emission. So you insist in talking about shocks, but it could be the photoionization of the AGN itself, right? Because in the BPT diagram, I mean, the points are okay.
Yeah, that's right. That's the next stage of analysis where we'll take that further and look at other line ratios, see if we can do, because you can make more diagnostic diagrams. I showed one. You can make several, and you can try and distinguish that. This was a quick first analysis, if you wish. But yeah, what I've said so far, it looks like it's AGN related rather than star formation related. Whether it's a jet or whether it's more like you say AGN induced physical processes in the gas, could be. Hopefully we'll see more from the other diagnostic diagrams. The thing is, of course, we also see this in kinematics. So there's a bit more than just the line ratios. There's also this offset in velocity and the higher velocity dispersion. So that all leads us to think about a jet rather than other mechanisms.
In the motivation of the talk, you have put a number of things which are very interesting, but in particular, I wonder, I mean, this galaxy, you have a circumnuclear starburst ring,
Yep.
right? And this is far from the place you have been measuring, right? Not very far, but not inside the field of view you have been. How far is the ring?
The ring is tiny. The ring is.
But at what distance is?
Oh, I'll show you. Where is it? There's the ring. It's sitting in there. That's it. It's what we call an ultra-compact nuclear ring. It's tiny. This is part of the ring. This little thingy there, that's part of the circumnuclear ring. It's tiny. I forgot the number. It's like a...
No, it's very small. I mean, it's far smaller than what I had in mind when I mean, thinking in circumnuclear rings, starburst. You know, what happened used to be a little bit farther. In fact, they used to surround the badge itself.
Right. This is just spiral arms in the galaxy.
Yeah.
This is not a ring. But the ring is sitting in there. It's tiny. It's what we call an ultra-compact nuclear ring. It's one of the smallest known nuclear rings. So it's really radius is, I think, between 100 and 200 parsec. I forgot the exact number. But it's actually why we chose this galaxy.
Okay, because in that case it's a little bit confusing because, I mean, there are other inner rings that happen to be surrounding somehow the bulge of the galaxy, that are called inner rings, which are a little bit bigger or small.
Sure.
Because in this particular case it's a pseudo ring, I mean, in the sense that it's ring-like, but it's not something we have to do with the patterns in the galaxy, resonance patterns or whatever related
It could
to
be.
that.
It could be.
It could be.
It could have to do, yeah. Because we find these, you talk about inner rings, but we find a lot of the mechanisms that cause inner rings mirrored in nuclear rings. And this is the small end, the small extreme end of nuclear ring distribution. Partly because it's what we can see. We don't have higher resolution than this. This is all, the rings, this kind of rings is found with HST imaging. And we can't really get much closer in. So this is what we can observe. This is the smallest nuclear rings we have. But a lot of the mechanisms seem to be similar.
But in that case, going back to your motivation, I mean, you are feeding something, right? From gas would come in from the bar, whatever. And in that case, this gas which is feeding the inner ring, that inner ring is also stopping the gas to get into the nucleus, right? So that is the passaging, right?
Sure.
No.
But again, it's the scale issue, because even this is a tiny nuclear ring, but it's still at least 100 parsec in radius. And remember, the AU fueling scale is AUs. It's just orders of magnitude different still. And you don't need a lot of gas. You just have some gas trickle through that ring and fall in. That's enough to fuel even the Seaford 1.9. But that's what makes this galaxy so interesting, that it's got both that tiny nuclear ring and then it's got all this outside structure with possibly a bar sitting there. And then it's got the AGN as well.
More questions? I have one question.
Yep.
Do you have velocity maps in a bigger field of view?
We should have one soon. We got the data with GAFAS, but we haven't made the velocity map yet.
Okay, because I wonder if when you look at the inner disk, you say that you can see that it's not oriented like the main disk, of your gas map, but maybe the gas velocity map is tilted there or modified because it's the inner region, and maybe when you look at the bigger map, maybe it matches and it's rotating like the
That's
galaxy.
one of the reasons why we took the GAFAS
Okay.
velocity field. What we've seen so far in velocity field is our own scale, which is this, and the ALMA data, which really don't go out much further. Where was the ALMA data? Oops, where's it gone? Here. This is the ALMA data. So really you don't go, you can see a bit here and you pick up a few other spots. I haven't found another velocity field, which is why we got our own. But yeah, certainly something we'll look at. Yes.
Any other question? Okay, let's thank Johan again. Thank you, Johan.